this lecture, we'll talk about how we'll do debugging using the Arduino. Specifically, how we're going to do observability, how we're going to get observability. So observing information about about what's going on when you're running the Arduino, when you run the code. Now, one way is to just look at the output pins, but we're actually we often want to see more important, more detailed information, let's put it like that. And so we need some way to transfer information from the Arduino or some microcontroller to the host that we're debugging from. And serial interface is how we're going to do that. So we'll talk about that right now. So serial protocol. So serial interface, basically, we're talking about a protocol, a set of protocols, really, that speak between the host and the microcontroller. And we're going to focus on serial protocol here, a serial protocol. Serial protocol, in general, is where you transmit data serially. Okay, so you transmit data one bit at a time, or one chunk at a time. In our case, one bit at a time. Instead of, say, 8 bits at a time. The Arduino, the microprocessor in there, the Atmega 328, it's an 8-bit processor, so each chunk of data is 8 bits. But we're going to be transmitting 1 bit at a time. So why would we do that? So the parallel data, 8 bits parallel, are going to be transmitted 1 bit at a time. The reason why we do this is because it saves us pins. Okay? So what has to happen is these parallel bits, these 8 bits, they're sent one at a time, and at the receiving end, they have to be received one at a time, but grouped back into 8 bits, right? We need the original 8 bits back. So they're received one at a time, and once it gets 8, it says, okay, this is a group of 8, that's a byte, and it sends it off and processes it. So we do this to save pins. Pin usage is important. So we mentioned this when we were talking about debugging. There aren't too many pins on these chips. Relatively, there are very few pins on these chips. So you don't want to have to use 8 pins for debugging if you can help it. You would rather use 1 pin. So that's why serial protocols are very common for this purpose, for debugging interfaces, because they don't use many pins. Now, they are slower, right? Because instead of sending all 8 pins in one clock cycle, you got to send 1 at a time. So it slows you down, but it saves pins, and pins are important. So pins are precious, and that's why we're using serial protocols in general. Now, there are many different, or rather several different serial protocols. We are going to focus on UART. UART stands for Universal Asynchronous Receiver Transmitter. It is an old protocol. Still useful, though. It's used for serial communication between devices. It gives you long distance, actually. It's asynchronous, meaning no shared clock. So what we mean by this is that, so we talked about what a clock is. A clock is basically a square wave, okay? And the square wave has rising edges and falling edges. And all the devices in the system time themselves off of the rising edge, okay? So one goal when you're using a clock is that every item, every, say, part that's receiving the clock, they have to receive the rising edge at the same time. So if you look at a circuit board, say you look at the motherboard of a computer, there's going to be a system clock. And this system clock, it goes to all the parts that receive clock, all the chips, let's say, on the motherboard. And the system clock is going to run at a certain frequency. And when the rising edge has to travel from wherever the clock is generated to the chip. And there's a certain amount of distance. Maybe it's traveling this far, okay? But these things are fast, so this far is a long distance, okay? So it is important that the rising edge arrives at every destination at the same time, or very close to it. That's the assumption for all of our systems, that all the parts on your device that are receiving the clock, they all receive the rising edge at the same time. Now, that's hard to guarantee in any kind of a big system, because even this much distance takes a certain amount of time to travel. I mean, even for light. And these signals are traveling a lot slower than light. I mean, if you think about how fast these signals are traveling, so just give you ballpark numbers, right? Take the speed of light, okay? Now, I don't remember the speed of light off the top of my head, but I happen to remember that, I know that the clock rate of a typical processor. So let's take a processor, let's say 1 gigahertz clock rate, okay? Now, that's a slow clock rate for a modern processor, or, for a desktop or something like that, but let's say 1 gigahertz. So if you have a 1 gigahertz clock rate, then you have a 1 nanosecond clock period. That means between 2 clock edges, you've got 1 nanosecond of time in between there. So then how far does light travel? Even light, which is the fastest. How far does light travel in a nanosecond? I don't know, about so far. Okay, I don't remember the distance. I'd have to compute it, but you can check into that. But it's some short distance, okay? this isn't a lot of distance, okay? And a motherboard can be bigger than this. So what this is saying is that in a clock, even the fastest signal can't travel from one end of the board, right? And remember that our electrical signals, are traveling a lot slower than light is. So the reason I bring this up is because guaranteeing that every device in the system receives a rising clock edge at the same time is extremely hard, because they're all different distances away from wherever the clock generation is. So it's very hard. And that makes UART a nice thing, because UART is asynchronous, meaning it doesn't have a clock. It doesn't require a clock. So that's a good feature of UART. Now, as a result of that, UART is slower than a lot of other protocols, and synchronous protocols might be, but it has that advantage that it can work over very long distances because it doesn't require them to have the same clock. So you get the longer communication distance. Clock skew is not a problem. So skew is basically, so like I said, that in a synchronous system, all the clock edges, all the components receiving a clock have to receive the clock edge at the same instant. But they never receive it at exactly the same instant. There's always a little bit of difference in the time when they receive it, and that difference is called clock skew. And you want to minimize clock skew, but clock skew isn't such a problem with UART because it doesn't have a clock. So ways that we use UART. So UART used to be much more used. Not so much anymore. It's been replaced by other protocols. But it was used by modems to connect to the network. So if you're old enough, you remember that people would actually when you'd connect to a network, AOL or whatever, CompuServe, you'd take a phone and actually connect it to your computer through a modem, through a big fat modem. And those things use UART, real slow communication and very long distance, but it worked. It was slow, but it worked. Computers used to have an RS-232 port standard. RS-232 is a port made to communicate with UART. They used to come standard. They don't do that anymore because UART has been sort of supplanted, taken over by other better, more effective protocols nowadays. So it's not well used outside of embedded systems and IoT devices like we're dealing with. It's still used in those domains for debugging mostly. But it's been replaced by things like USB, Ethernet connections, I2C, SPI. We'll cover those later. But there are a lot of other options that you can use instead of UART nowadays. But it's simple. UART is a very simple protocol, and it's low hardware overhead. That's another reason why people still use it in embedded systems for communication, for debugging, and things like that. So it's just so convenient to use. And it's built into most microcontrollers. So most microcontrollers have hardware support for UART, so why not use that for debugging? Thank you.